Saxon Advanced Math Lesson 80. This is a second version of the Trig Identities lesson. And in this lesson, we're going to do a little bit of review. And from there, we'll move forward with understanding some of our newer identities. So as we look at this, we have to keep in mind that these are review. We already know sine, cosine, and tangent. And we already know that their inverse functions exist. One over the cosecant, one over the secant, one over the cotangent. We also recognize that we can get cosecant by itself by a little bit of algebra here and say 1 over the sine. The secant is 1 over the cosine. The cotangent is 1 over the tangent. And then we also have to add into those our new, which is our even odd identities, which says that the sine of negative theta is the negative sine of theta. But the cosine of negative theta is the cosine of theta. Remember, that was because this is an even identity and this is an odd. Then we added these two here. They just kind of threw those in. If you look at those, the tangent of theta, of negative theta, is the negative tangent of theta, which means that tangent is an odd function as well. And then we come up with each one of their inverses. So the sine can be related with the cosecant, and that works out as well. The cosine with the secant and the tangent with the cotangent. Now, these identities look hard, but these are just stuff that we've already used. So stop a minute and just realize these are things we've already done. We're just going to start applying those into showing one type of a form into another. We're just doing some conversion, almost like unit conversion. Remember that identities are almost like unit conversions. Like if I said how many miles is something away, I could tell you how many meters that was. And you say those numbers aren't the same. Well, no, the numbers aren't the same because we're using an identity that says here's exactly how many meters are in a mile, or exactly how many inches are in a foot. And those are identities. And that's what we're working with here. Now, we have 3 new identities that we're going to pay attention to. This one is new in this year. However, if you've taken Saxon in the past, or maybe another book in the past, this one is usually introduced somewhere in the geometry book as well. So the sine squared theta plus the cosine squared theta equals 1. Now, we're going to take just a moment and show why that is. So we are going to go back to our old friend, the theorem here, our Pythagorean Theorem, which says a squared plus b squared equals c squared. And then we're going to define using this triangle. And the reason why we're using a triangle with only letters is because it works as an identity, and it always works no matter what those letters are, as long as it's the right triangle. So we're going to go ahead and set that up and say, well, the sine of theta. So we assigned our corner here to be theta. And we said the sine is opposite over hypotenuse, so a over c. The cosine adjacent over hypotenuse, b over c. And the tangent opposite over adjacent, a over c. And I have these 3. Now, we're going to rewrite this down here, and then we're going to start plugging these in. Well, I already know that what is sine squared theta. And keep in mind, this isn't the sine squared, it's the sine of theta. Whatever that numerical value is, squared is what that works out to be. Well, what is sine? Well, the sine, once again, opposite over hypotenuse, or a over c. So we're going to plug in, for this right here, we're going to plug in a over c. And we're going to square it because the whole term is squared. And then we're going to say b over c for the cosine. That's adjacent over hypotenuse, right? And those are your a and your b, right? That's how this is going to work, your a over c and b over c. If I square these out, a times a is a squared, c times c is c squared, b times b is b squared, and c times c is c squared. Well, I have a common denominator, so I add them up, and I say a squared plus b squared over c squared. But I remember something. A squared plus b squared equals c squared. So if I substitute in my a squared plus b squared in for that c squared, I end up with c squared over c squared. Well, c squared over c squared is 1. And that's how this identity works. Now, this is one we will use quite often. So you want to make sure you memorize this one for sure. Okay, sine squared theta plus cosine squared theta equals 1. The next 2, and we'll see how these work in play, I'm going to go ahead and show you how we get this one. 1 plus a cotangent squared theta equals the cosecant squared theta. So I'm going to just rewrite this and realize that 1 plus cotangent squared theta, right, here we are, that's just from down here, that's going to equal 1 plus, well, what is cotangent? Cotangent is the reciprocal of the tangent, and the tangent is a over b, so the reciprocal of a over b is b over a. So we plug that in. Okay? So 1 plus b over a squared. Well, this becomes b squared over a squared, right? And so now I have 1 plus b squared over a squared. If I need a common denominator to add these up, I can rewrite 1 as a over a, and when I add them, I'll end up with a squared plus b squared over a squared, right? Because this was b squared over a squared, and this is 1, so it's anything I want it to be, right? And I decided I needed a common denominator of a squared, so a squared over a squared, and that gave me my a squared plus b squared over a squared. Well, what is a squared plus b squared? Pythagorean Theorem, that's c squared, so I plug that in. C squared over a squared. Now this is where a lot of people get confused, so pay very close attention to this. Right here, I can rewrite this as this. These mean the same things. I am simplifying this, if you will. So, and a lot of times at trig identities, you have to recognize some patterns. And this is one of the patterns we're looking at. We realize that c squared over a squared really is c over a times c over a, which is c over a squared. Well, what is c over a? Well, a over c is the sine. So c over a is the cosecant, and that is the cosecant squared, because we're squared, right? So that's the cosecant right there, and that's squared. Well, is that what we're trying to prove? Sure is, cosecant squared theta. Moving to our last one, we'll walk through this one. Tangent squared theta plus 1 equals secant squared theta. We're going to do the same thing here. We're going to say, what is tangent? Well, the tangent is, in this triangle here, right? What is tangent? A over b. So I plugged in my tangent. Then I square it. A squared over b squared, right? This is once again where I'm paying attention. I can rewrite this 1 as b over b squared, because that's what b is, right? And I can say, therefore, it becomes a over b squared plus b over b squared, and that gives me common denominators. Now I can say a squared plus b squared over b squared. I already know what a squared plus b squared is. That's c squared, and I plug it in. I end up with c squared over b squared. Well, if I did the same thing I did right here with separating that out, I end up with c over b. Well, c over b, what is c over b? C is hypotenuse, b is adjacent. Well, what is the adjacent over the hypotenuse? Well, that's the inverse of the the hypotenuse over the adjacent. That's the inverse of the adjacent over the hypotenuse. What is adjacent over hypotenuse? Well, that's going to be what? Hypotenuse over adjacent has got to be my secant, and it works out as secant squared theta. These are identities, and we're going to use them throughout. Let's go ahead and look at the other ways of writing these identities. Now, don't get confused that this is a bunch of writing, okay? And because when we get down to it, it's really not that bad. This is our original. We could rewrite it by moving the cosine to the right-hand side, right? Sine squared theta equals 1 minus the cosine squared theta. Or I could go ahead and get cosine squared theta by itself, right? By moving the sine to the other side. And that's what we did over here, by subtracting sine squared theta from both sides. And I can do the same thing with each one of these. The problem is this gives us 9 more things to memorize. You don't have to do that though. Memorize this one. And that's why I said it right here. You need to memorize that. And the reason is I can very easily get these into other trig functions. For instance, if I just took everything here and divided it by sine squared theta, I would end up with 1 over cotangent squared theta equals the cosecant squared theta. 1 plus the cotangent squared theta. Oh, look at that. So just by dividing everything by the sine squared theta, I end up with the second identity. If I go to the third identity, if I want this one, I can divide everything by the cosine squared. Sine over the cosine squared, right? Cosine squared over cosine squared is 1, and 1 over the cosine squared. Well, what is 1 over cosine squared? That's the secant. What is the sine over the cosine? That's the tangent. And I can very easily derive each one of these as I need them. Instead of having to memorize 9 things, I memorize 1. I can derive these 2 from it by dividing by what? Sine or cosine. And then I can get any of these other ones just by solving for which variable I want, or which term I want by itself. Look at 80.1, and we're going to do this together. Show that the secant squared of x minus the tangent squared of x over 1 plus a cotangent squared of x equals the sine squared x. Now, that scares people. I get it. Where did this x come from? And the book didn't do this on accident. It was not accidental. They threw an x because x is an unknown value, just like theta is an unknown value. They just want to make it so that you're realizing it doesn't matter if that's a real letter or a variable or a number. It doesn't make a difference. It always works the same as long as those are all the same. Well, they're all x's, so that all works. Okay? Let's work with this together as we get through this. One, we're going to just take the numerator first. What do I know about the numerator? Secant squared theta minus the tangent squared theta is 1. Where did that come from? Well, that's one of my identities. So if I realize that, I can say, oh, I'll take this and make it into a 1. Boy, that made it a lot easier. And I know that 1 plus the cotangent of squared theta, or 1 over cotangent, or 1 plus cotangent squared x, that's going to be what? My trig identity, looking at the board, you're correct, it is the cosecant of x. So I'm going to go ahead and plug that in and say that's the cosecant, right? Right here. So I can plug in cosecant squared x. Well, what is the cosecant? Well, once again, we're going to look at our big chart here and find cosecant. What's another way of saying the cosecant? Well, what is the cosecant? Well, that's the 1 over the sine, right? Which we should have memorized. So I'm going to say 1 over sine squared x. Now I have 1 over sine squared x. Remember that if I invert and multiply the top and the bottom, I end up with sine squared x. Wait a minute. That's what I was trying to get. And it works. That's how these trig identities work out nicely. All you're doing is plugging in on one side. You're picking a side and you're plugging in values that you know from these derivatives that you have, from these options, and you're going to gain back to an answer that works. Oh, it's sine squared theta, because they're identities. Just like if I said convert 60 miles per hour into feet per second, you would have to know some identities. The identities you'd have to know: how many feet are in a mile, how many seconds in a minute, how many minutes in an hour. And oh, how do you know how to do this? Well, I get to where I'm trying to get to. I look at that first and I say, how can I break this down and convert it into things I know? And these are all my conversion factors. It's one way to look at that. Okay, last example. Show 80.2, this example 80.2, show 1 over tangent of A plus the tangent of A equals the secant A cosecant A. This one's easier because I already know 1 over the tangent. Well, what is tangent? Tangent of A, we already remember this. This is one of our standard ones, is the sine over the cosine. So, and part of my problem looking at the board is, yeah, it's confusing to me as well. There's a lot of stuff up there. But what's not confusing is I'm looking at saying, oh, I remember what the tangent is. And that's why it's so important you memorize these functions and memorize these identities, because otherwise you're looking at saying, I don't remember, where do I even start? Well, tangent is sine over cosine. And I'll answer that in a minute. I'll go back to that. 1 over the sine over the cosine. Well, 1 over the sine of the cosine. Well, look at that. And what is the tangent? Well, it's sine over cosine, so I plug it in here. Then I realized that if I find 1 over that, I would invert it, and I end up with cosine A over sine A plus sine A over cosine A. Well, if I wanted to add these, I need a common denominator. This is just general math now, right? Well, what's this one missing? Cosine. What's this one missing? Sine. So I multiply the top and bottom of this one by the cosine, and the top and bottom of this one by the sine. When I do so, I'll get cosine squared and sine squared. Oh, cosine squared plus sine squared over sine A plus cosine A. But what is this? I know the cosine squared plus the sine squared equals 1 for my identity up there. So I plug that in and I say 1 over the sine over the sine A cosine A. Well, if I split that into two fractions, I'll say 1 over the sine times 1 over the cosine. Well, what is 1 over the sine times 1 over the cosine? Well, 1 over sine is the cosecant, and 1 over cosine is the secant. I skipped the C there, I apologize. 1 equals the secant. And therefore, I can say secant A times cosecant A equals 1 over sine A times 1 over cosine A. Well, wait a minute. That's what I was trying to get, right? And there it worked. And now, keep in mind, this is the simplest way to get to the answer. There isn't a right or a wrong way on an identity as long as I'm not breaking any of the rules. In other words, there are other ways you may find to get from point A to point B that are also acceptable because you have already memorized some of these identities, or because you see, I don't want to say a shortcut. A good example, going back to my converting 60 miles an hour into feet per second. If I remember, oh, my identity is 60 seconds in a minute and 60 minutes in an hour, but I remember that there's just 3,600 seconds in an hour, so I use that as a conversion factor. Is that wrong? No, it's just not a common one. And you're going to find uncommon identities that pop up in here that you're like, oh, I use this so often, why don't I just use it? And you certainly can, and will get the correct answer and showing that as the identity changes.